Okay, so in order for you to understand the concept of simple linear regression, first you need to know the concept of correlation. Have you learned about correlation analysis? Tak apalah. Yeah, correlation.
Is it relationship between two variables?
Yes, relationship between two variables. So relationship between two variables is correlation. Linear regression is just an extension of correlation analysis. Okay? So let's look at correlation and simple linear, the similarities and differences between correlation and also linear regression. Okay, both correlation and simple linear regression look at the relationship between two numerical variables. Okay? Both measure strength and direction of linear association, but correlation and regression serve different purpose. Okay? This is a scatter plot of correlation between random blood sugar and also cholesterol. Okay? When we graphically explore relationship, normally we plot a scatter plot. Okay, this one a scatter plot between RBS and also total cholesterol. Okay, so visually you can look at the relationship between these two numerical variables. Correlation look at the strength, the direction, and also strength of linear relationship between variables. For example, here we can see that there's a linear relationship between RBS and total cholesterol. Okay, and the relationship is positive. Okay, increasing level of random blood sugar, total cholesterol also increase. So the relationship is linear. Okay, in regression analysis, it has all the qualities of correlation analysis, plus the ability of predicting changes in the outcome variable based on changes of the independent variables. Okay, it has also the abilities to determine how many percent variation in the outcome variable, which can be explained by the independent variable. Okay, meaning that here, correlation analysis only look at the direction and also strength of linear relationship. Okay, correlation analysis does not concern with prediction. When we are not interested with prediction, it does not matter which one is the independent, which one is the dependent variable. Okay? Whereas for regression analysis, we are trying to predict total cholesterol, the dependent variable, based on one independent variable, RBS. So we are trying to predict total cholesterol level based on random blood sugar. Okay? For correlation analysis, it does not matter which one is the independent, which one is the dependent variable. Whereas for regression, for linear regression analysis, you must be sure which one is the independent variable, which one is the dependent variable. In regression analysis, your interest is to see for one unit increase in the independent variable, how much increase is in the dependent variable. Okay, for example, if the random blood sugar increased by 1 unit, how much increase in total cholesterol? Okay. For regression analysis, the ultimate objective is for prediction or estimate the value of one variable corresponding to a given value of another variable. Okay. So here you can see that for a regression analysis, you need to have a regression line. Okay. The regression line, we call it the best fit line. And the regression line can be represented by a regression equation. For example, here the regression equation based on this regression line is y equal to 0.1441x plus 4.2984. So it means that y is the dependent variable, total cholesterol, x is the independent variable, RBS, So this regression equation means that for every 1 unit increase in random blood sugar, the total cholesterol level will increase by 0.14 for 1 unit. Okay. So these are the differences, the similarity and also differences between correlation and also regression analysis, linear regression. Both assess linear association between the two variables. Both assess strength and also direction of relationship. Correlation analysis, it does not matter which one is X, the independent variable, and which one is the Y, the dependent variable. Whereas for regression analysis, you must be sure which one is the X and which one is the Y dependent variable. Okay? Regression analysis also, you can identify important predictors for Y. You can identify whether X is an important predictor for Y or not. Okay? So if X is an important predictor, you can predict Y based on X. Okay? And you can also examine the effect of one or more variables toward the outcome variable after adjusting for other variables. So this one, when you do multiple linear regression, you are examining the influence of one independent variable towards an outcome variable after other independent variables were adjusted. Okay? So this slide is important. You need to remember this slide. So this one must come up in exam.
One question, Doctor.
Yes.
When coming to reporting,
Okay.
we use the word positive outcome and positive relationship between variables.
Okay.
And then the other one is normally we say there is a significance relationship between two variables.
Okay.
So just want to know whether for correlation, is there any particular word that you use? And for regression, is there any different type of reporting for it?
So for correlation analysis, the term correlation must be there. Okay, the term correlation must be there. For correlation analysis, we report the direction, okay, the strength, and also the significance of the correlation. Direction. So first we look at the R value. R here, R equal to 0.884. Okay. So the R value is positive, indicating a positive relationship. Okay, so here R 0.884 is the sign is positive value. So it indicates positive relationship between RBS and total cholesterol. The value of R is 0.884. So value of 0.884 is considered to be a strong relationship. Okay? And whether the correlation is significant or not, we need to look at the P value. Okay? So P value here is 0.0000. We in writing we write as less than 0.001. Okay? So this result can be interpreted as there is a significant positive, there is a strong positive correlationship. Okay? So strong based on 0.4. Okay? Positive based on the positive value. Okay? Strong positive relationship between RBS and also cholesterol, and the correlation is statistically significant at P of less than 0.001. Okay, that is how we interpret correlation analysis. Okay? So always remember the strength, direction, and also whether it is significant or not statistically. Okay, that one is for correlation. Whereas for linear regression analysis, normally we interpret as association and not correlation. Okay?
Okay, Doctor, thank you.
Okay, so any other question? Okay, so we proceed. Okay, so regression model is used to fit a straight line through the data, where the regression line is the best predictor of the outcome variable using one or more explanatory variable. Okay, two main purpose in building a regression model. The first one is to build a predictive model, and the second one is to examine the effect of an exploratory variable on an outcome variable after adjusting for other important explanatory variable. So the second one is mainly involved in multiple linear regression analysis. Okay. So this one, okay, we have covered previously. So let's jump into simple linear regression. Okay, it is a type of univariable, univariate parametric statistical analysis. Okay, this one have been covered in Introduction to Statistics. Yeah, right. Okay, you know what is univariable, what is univariate. Univariable means that you have only one independent variable. Univariate means that you have one dependent variable. Okay? Parametric concern with normality of your data. Okay? So for parametric types of statistical analysis, your data need to be normally distributed. Okay, in simple linear regression, we want to predict y based on x using a prediction line. Okay, so be careful in terms of regression line. It is different between correlation and also linear regression. When you do correlation analysis, there's no need for a regression line. And this is a common mistake. Okay, people do correlation analysis and they include in a regression line. And the regression line is only appropriate for regression analysis. Okay? Why? Because the regression line is a prediction line. Okay? When you want to predict one dependent variable based on one independent variable, then this regression line is appropriate. Okay? Based on this regression line, you can come up with the regression equation. Okay? So now we are predicting the dependent variable based on one independent variable using this regression equation. Okay, so let's explore the meaning of this equation. So the equation can be written as y equal to a plus bx. During our secondary school, we call it y equal to mx plus c. All right. Okay. Both similar things lah, right? So y equal to a plus bx. Y is the outcome variable. X is the independent variable, A is the intercept, and B is the slope. Okay, the slope or the gradient. Okay, A is the value of y when x is equal to 0. Okay, it can be either positive or negative. And B is the slope or is the slope of gradient ratio between the changes of y and the changes of x. Okay, this one is for manual calculation, but using software, all these things are given. The slope indicate how many unit changes in y as a result of one unit changes in x. Okay, so remember I've mentioned about assumption, the validity of statistical model. Okay, so to check validity of this of linear regression model, you need to check this assumption. Okay, so the result of linear regression will only be valid if these assumptions are fulfilled. Okay, so the result is valid if the samples are randomly selected, if the y values are independent of each other, the outcome variable is numerical, the relationship between x and y is linear over the range of values. This one, normality of the dependent variable, the subpopulation of y value within each value of x must be normally distributed. And lastly, the dependent variable has equal variance at each value of x. Okay, any question? No, sir. Okay. So everyone can visualize this thing, right? Assumption. Quite difficult to remember lah. Okay, never mind, don't worry. I show you one by one. Okay, it seems like you need to check many assumptions, but actually the first three assumptions must be settled during design. Must be settled during study design. For example, random sample, the decision to take your sample randomly or not must be decided during study design. Independence observation, the decision whether all the measurements are independent of each other or not need to be decided during design. And the scale of measurement of your outcome variable also need to be decided during study design. Okay, so during analysis, actually you need to check only these three assumptions. Okay, only these three assumptions need to be checked. Linear relationship between variables, normal distribution of y in any point of x. Okay, this is assumption of normality. And lastly, assumption of equal variance of y in any point of x. Okay, so how you can check these three last assumptions? Simply by using a scatter plot. Okay, by using a scatter plot, you can visually inspect these three assumptions. Okay. For example, you want to explore relationship between x and y. Based on this scatter plot, the aim is to get an elliptical, more or less elliptical shape in distribution. So elliptical shape of distribution, of the scatter plot distribution, suggests that the relationship between x and y is linear. Okay, so assumption of linearity. Assumption of normality, it means that normal distribution of y in any point of x, it means that within each value of x, the value of y is more or less normally distributed. Okay, and also equal variance. At each point of x, the value of y is more or less, the dispersion of y within each value of x is more or less equal. Okay? So as long as you get an elliptical shape, when you plot scatter plot, then you can assume that these three assumptions fulfill. Okay? So your model fulfill these three assumptions. Okay, so very simple for simple linear regression. So assumptions are related when you have this kind of scatter plot. Okay, this scatter plot suggests non-linear relationship between x and y. Okay, and whereas if you have this kind of relationship in scatter plot, it suggests that the data the data violates the assumption of non-constant variance. So here you can see that the dispersion of y increase as the value of x increase. Okay, so initially, as the dispersion is very small. Okay, when the value of x increase, the dispersion become larger. Okay, so in this situation, the assumption of non-constant variance is violated. In this condition, the assumption of linearity is violated. Okay, here, very simple. Okay, the steps in conducting a simple linear regression, or the steps in modeling a simple linear regression involve all these 6 steps. Okay. The first one involves exploratory data analysis. You explore the data, you check the distribution, both quantitatively and also qualitatively. You do descriptive statistics, and most importantly, you explore the relationship using scatter plot. The next step involves getting a regression line using least square method. The third step is to evaluate the regression line. Okay. So the regression line, remember, involve 2 components, right? There's 2 components in regression line. One is the intercept A and also the slope beta. So we evaluate both the intercept and also beta regression, the regression coefficient, or we call it slope. Okay. Next thing, we evaluate the model fitness. We check the assumption. So if the model is fit and all the assumptions are fulfilled, then only we can conclude, we interpret, and also we present the results. Okay. Okay, so I show you the steps of analysis. Later on, I give you the lecture note and also the data set for you to do exercise on your own. Okay. Okay. Okay, so this is the data in SPSS. Okay, we have 2 variables here, length and also head circumference. Okay, for example here, a researcher would like to know, is there any relationship between length and also head circumference? And also the researcher would like to predict, one variable. For example here, length and also head circumference. Yeah, the researcher would like to predict length, the baby's length, okay, based on the baby's head circumference. Okay, newborn being delivered. Okay, the researcher would like to determine whether the length of the baby, okay, can be predicted based on head circumference. Okay, so the first step in doing the analysis is to do data exploration. Remember, do data exploration, determine distribution, do descriptive statistics, and have a look at the scatter plot. Okay, so the first one is to do descriptive analysis, to do exploratory data analysis. Okay, so very simple. Go to analyze, descriptive, and also explore. So we explore both variables, okay, both numerical variable. So I just click OK. Can you see the output here?
Yes.
Yes, Doctor.
Okay. So just in SPSS, it is very easy. Just by clicking a few buttons, you already get the result. Okay, so the first one, case processing summary, is to show whether there's any missing data or not. Okay, so for both variable, there's no missing data. Okay, so you're happy. Next one is to look at the descriptive statistics. Okay, mainly is to look at the distribution of both variable. Okay, Okay, so remember normality distribution. Okay, for normality distribution, we examine the distribution of both variable. Okay, so this one during lecture on descriptive, you have lecture on descriptive statistics or not? Introduction to SPSS. You have unit on how to decide normality. You need to know how to decide normality based on this table, descriptive statistics. Okay. So, for example, my approach of deciding normality, both quantitative and also qualitative. So the first method, I look at the quantitative component. So I look at the mean and also median. For a normally distributed data, the mean and median must be more or less equal. Okay, so here mean and median more or less equal. Okay, the standard deviation is less than half of the mean. The skewness value and kurtosis value is within plus minus 1. Okay, so those values suggest that length is normally distributed. Same thing for head circumference. Mean and median is more or less equal. The standard deviation is less than half of mean. The skewness and kurtosis value is within plus minus 1. So all those things suggesting that head circumference is normally distributed. The next thing is I look at the test of normality, Kolmogorov-Smirnov, and also Safirovic test. We prefer Safirovic test over Kolmogorov-Smirnov. Okay. For Safirovic test, a significant p-value suggests that the variable is non-normally distributed, is skewed. Okay. So for example, Safirovic test, length and head circumference, both the tests indicate that the distribution is non-normal. Okay. So it contradicts with other quantitative measurement just now. But be careful in interpretation of Safirovic test. Here you have very large sample, 550. When the sample size is very large, Safirovic test is too sensitive to outlier. Okay? When there's presence of, even if there's a slight deviation in normality, Safirovic test will suggest that it is non-normally distributed. Okay? So normally, if the sample size is too large, we don't rely much on Safirovic test. Okay? So we proceed to qualitative measures of normality. We look at the histogram with overlaid normal curve. Okay? We insert an overlaid normal curve over the histogram. So we obtain a very nice bell-shaped curve, which indicates that the data is normally distributed. And also we look at the box and whisker plot. We search for presence of outliers and also extreme outliers. Okay? So here we can see there's one outlier, no extreme outliers, and the pattern of this box and whisker plot suggests that the data is normally distributed. So length, for variable length, quantitative measures, quantitative exploratory data analysis suggests that it is normally distributed. For head circumference, histogram with overlaid normal curve also indicate that it is normally distributed. And box and whisker plot also indicate normality, as evidenced by no outlier and also no influential outliers. Okay. So next we can go with building the scatter plot. Okay. Just plug in simple scatter plot. Okay. So now we are going to predict length based on head circumference. So the y-axis must be length, the x-axis must be head circumference, and click OK. Okay, so here you can see an approximately elliptical shape in relationship between head circumference and length, and we can see that the relationship is more or less linear, okay, with more or less normal distribution of y at each value of x, and also the dispersion of y within each value of x is more or less equal. Okay, so that's how we assess linearity and also equal variance, and also normality plus minus based on scatter plot. Okay, so very simple. Okay, so elliptical shape of scatter plot suggests assumption of linearity, normality, and equal variance assumed. Okay, so when the assumption is fulfilled, when all assumptions are fulfilled, then we can be sure that any statistical model derived from this data will be valid. Okay, so now what we need to do is to insert line to the scatter plot. Add fit line. Okay, so by adding a fit line, we call it regression line, then we have the regression equation. Okay, so this is the regression equation. Y equals to 14 plus 76, 14.76 plus 1.06 multiplied by x. So it indicates that for every 1 unit increase in head circumference, the length will increase by 1.06 unit. Okay? Okay. So the next step is to evaluate the regression line. Okay, so the second step is to construct a regression line using least square method. So this one we have performed this step. Okay, we have inserted the regression line and we have obtained the regression equation. Next is to evaluate the regression line, okay, both the intercept and also the slope. Okay, so here we only have the intercept and also the slope. So it is important to assess whether this slope is significant or not. Okay, so how to evaluate? We perform the linear regression analysis. So how to perform linear regression? Go to analyze, regression, linear. Okay. So by default, you'll be given this GUI. Okay. So you need to put in the dependent variable. Now length is the dependent variable. Head circumference is the independent variable. Under statistics, ask for 95% CI of regression coefficient. Okay, you can ask also for descriptive statistics. Okay, and also other square changes. Okay, so the rest of this thing, no need, don't bother first. Okay, then just click OK. Okay, this is the descriptive statistics for length and also head circumference, the mean and also the standard deviation. This table can be obtained, the information from this table can be obtained from the descriptive table just now. Okay, same thing. Okay, this table of less interest just show correlation between head circumference and also length. Okay, so the correlation between head circumference and length is 0.598. positive. So there's a positive, moderate, some say strong correlation between head circumference and also length. Okay. So we are interested with this table only. Now we are interested with this table only. We need to evaluate constant. Constant is the intercept and also the slope here. The unstandardized coefficient beta for head circumference is the slope. This one is the intercept. Okay. Okay, testing the slope. Testing the slope is important to determine if X is an important predictor of Y. Okay? So if you are doing exploratory types of modeling, then this step is important. Okay? We need to determine whether this variable is an important predictor for Y or not. Okay? When there's no linear relationship exists between X and Y, the slope, this value, should be horizontal. The beta should be 0. Okay? If the null hypothesis of beta is rejected, it indicates that there is a linear relationship between X and Y. X is able to predict Y. X is an important predictor for Y. And it also indicates that there is a good fit of data to a linear model. Okay? So how to decide whether to reject or not to reject null hypothesis for beta equal to 0? We look at this p-value. Okay? The p-value for this side. Okay? The p-value for X, for head circumference. So now the p-value is less than 0.05. So we can reject null hypothesis. So rejecting the null hypothesis here indicates that head circumference is an important predictor for length. Okay? It means that you can use head circumference to predict length. This variable is an important predictor to be included in the model. Okay? And also, including this variable has a good fit to a linear model. Okay? So we can simply say that this variable is an important predictor for the outcome variable. Okay? Testing the intercept is of less important. Why? Because we are not going to interpret the intercept. The intercept here is the value of length when the head circumference is 0. Right? So we are not going to predict what is the length of one baby if the head circumference is 0. Because clinically it is impossible for head circumference to be 0. So we are not interested with evaluating the intercept in this case. Okay? Okay, so next we proceed to step number 4, model assessment. We evaluate how good is the model or how fit is the model. Yeah? The method is by looking at sum of square of error, the significance of regression, and also model adequacy. Yeah? So when we perform the linear regression under statistics, by default, model fit has been checked. Okay, so make sure this is checked. Okay. Okay, so this table and this table both measure model adequacy. Okay, model summary and also ANOVA table. Okay, make sure you are given, you can obtain these two tables, model summary and also ANOVA. Okay, model summary. Okay, R is the correlation between both variables. R square is just the square of the R value. Okay, adjusted R square for simple linear, normally we don't bother to look at the adjusted R square. Adjusted R square is the value of R square adjusted for the number of variables included in the model. Okay, so if you have only one variable, both R square and adjusted R square will be more or less equal. Okay. Standard error of estimate, smaller error indicate better model. So this one, if you are comparing few models, so you can compare R square, adjusted R square, and also standard error of estimate. Okay, so if you have only one model, then there's no comparison to be made. Then you need to just interpret the R square. Okay. The sum of square of error, it indicates the amount of error in your model, So less error indicate a better model. So similarly, this one, we focus on this one if we are comparing between several models. If we have only one model, then there's no need to evaluate the sum square of error. But smaller error reflect a better model. Okay, so significance of regression indicate how significant is our regression. How significant is our regression model? Okay, a significant regression model, the ANOVA value must be less than 0.05. Okay, so our model, the model obtained is significant if the ANOVA result shows a significant p-value. Okay, so ANOVA evaluate the model. Okay, this one, the coefficient evaluate the variable. Okay, so since we only have one variable, so both the p-value for coefficient and also p-value for the model will be same. Okay, so sum square error, less error, better prediction line. Significance of regression. Okay, so if it is significant, it indicates that the regression model is significant. The model adequacy, we look at the R square value, adjusted R square, and also standard error. Okay, most importantly, we focus on R square because as I mentioned before, one important aspect of linear regression is to evaluate the importance of one independent variable towards an outcome variable. Okay, to decide whether it is important or not, the influence, the magnitude of influence, we look at the R square. The R square describes how many percent of variation in Y which can be explained by X. Okay, how much variability in the dependent variable which can be explained by X. If everything regarding Y can be explained by this one independent variable, then the R square value will be 100%. The other way around, if none of the variation of Y can be explained by this one independent variable, then the R square value becomes 0. So R square can range from 0 to 1. So 0 means 0%, 1 means 100%. Higher R square value, it indicates better fit of the model. So in this table, in this result, for example, just now, okay, we have we obtain R squared of 0.358. It indicates that 35.8% of the variation in length okay, can be explained by head circumference. So it means that head circumference can predict 35.8% variation of length. And the rest need to be explained by something else, by other variables. So again, assumption for linearity, normality, and also equivariance. Okay, we can check using scatter plot, I mentioned just now, but you can also check this assumption by examining the residual. Okay, so what is residual? Residual is the differences between observed and also predicted value. Okay, when you plot scatter plot, this is the expected value. This is the, for example, this one. This is the observed value. Okay, for each point of x, there's one expected value, one observed, one predicted value. The difference between observed and predicted value is the residual. Okay, so assumption for linear regression using residual is also called residual analysis or residual diagnostic. And in order to do residual diagnostic, you need to generate residual with predicted value. Okay, so how to do it? Again, we run the analysis. Under safe, click unstandardized predicted and also unstandardized residual. Under line. Okay, so two variables will be generated. One is predicted value, the other one is residual value. Okay, so for assumption of linearity, you can check using scatter plot of residual and predicted values. So we call it XPYR or XPRY. Okay, same thing. Okay, so scatter plot of XPYR can be used to check assumption of linearity and also assumption of equivariance. Whereas normality assumption, normality of the dependent variable can be checked using histogram of residual and also box and plot of residual. Okay, so here you need to plot three things. One is XPYR, histogram of residual, and also box and whisker plot of residual. Okay, so now you have generated the residual. So what we need to do is to plot scatter plot of XPYR. Scatter plot, simple scatter, X predicted, Y residual, then click OK. Okay, so you will be given this scatter plot, and you need to add reference line at 0. Okay, reference line at 0. Okay, so we add reference line at 0. Okay, so the assumption of linearity and equivariance assume if all the residuals are scattered randomly around the zero line. Okay, so if all the residuals are scattered randomly around the zero line, so it indicates that the linearity and equal variance assumption fulfilled. Okay, so very simple. So these are the relationship. What will happen if your data violates the assumption of linearity? Okay, so if your data is linear, if the relationship between x and y is linear, this is based on the usual scatter plot, x and y. When you plot XPYR, you get this kind of scatter plot. If your data, x and y, show curvilinear relationship, when you plot XPYR, also it will show curvilinear relationship. Assumption of homoscedasticity or assumption for equal variance. If your data have equal variance, your XPYR plot also shows equal variance scattered randomly around zero line, more or less equally around zero line. But if your data has non-equal variance, your XPYR also will indicate non-equal variance with increasing residual with increase of x. Okay, so if your XPYR scatter plot shows this kind of shape, it suggests that the relationship is the variance is not equal throughout the value of x. Okay. So the second plot you need to plot is in order to check normality assumption. So you need to check assumption of normality based on residual. So just plot histogram. Plot histogram of the residual with normal curve. Okay, so it shows a nice bell-shaped curve indicating normality of residual. And another graph is box and whisker plot of the residual. Okay, we show box and whisker plot of the residual. Okay, so box and whisker plot and also histogram of residual indicate normality assumption fulfilled. Okay. XPYR scatter plot of X predicted Y residual indicate that assumption of normality, linearity, and also equal variance assumed. Okay, so last step is interpretation, conclusion, and also presentation of result. So we need to look back at all the results performed previously, all the analysis performed. Okay, so mainly focus on the coefficient table. So the regression coefficient for head circumference is positive. And why positive? Because the beta is 1.06. The 95% CI does not include 0. Okay, 0.9 to 1.17 does not include 0. And the p-value, if the 95% CI does not include 0, the p-value must be significant. So here the p-value is less than 0.001. So our decision now is to reject the null hypothesis of beta equal to 0. So we conclude that head circumference is an important predictor for length. There is a statistically significant linear relationship between head circumference and also length. With 1 cm increase in head circumference, length will increase by 1.06 cm. Okay, we can, based on R square also, you need to interpret that 35.8% of the variation in length can be explained by head circumference. If your interest is for prediction, you can produce the regression equation. Y equal to 14 plus 76, y equal to 14 plus 76 plus 1.06 times head circumference. So you can predict what is the length of a baby if the head circumference is 40 cm. So if the baby has a head circumference of 40 cm, then we are predicting that the length is 50.16 centimeter. Okay. In terms of presentation, you can either present your result in table, text, or graph. So normally we prefer text table or graph. We prefer table presentation. Okay. So we prefer statistical result to be presented in tabular format. So here, you need to include the beta, crude regression coefficient. Okay, why crude? Because it is simple linear regression. For multiple linear regression, later we see that we replace this crude regression with adjusted regression coefficient. So beta is 1.06, the 95% CI 0.94 till 1.18. The T statistics obtained from this table, okay, this value 17.45. For it, okay, the P value less than 0.001 and the R square 0.358. Okay, that is how you present your result of simple linear in a table. Okay, in summary, steps in modeling a regression, linear regression model. Okay, the first one, to answer the question of how to predict Y based on X, you construct a regression line. To determine, you need to determine whether X is an important predictor of Y or not. You test the regression line and test the regression equation. Can the regression line be used to predict Y? You test the model fitness. Will the result be valid? You check the assumption based on either the ordinary scatter plot or based on residual diagnostics. But we prefer residual diagnostics. Why? Because in multiple linear regression, all assumptions will be made based on residual diagnostics. Okay, that's all. Thank you. Any question? Any question? After this, I will share the slide and also the data set.
Hi, I'm still trying to grasp the difference between the first part where you showed the scatter plot and then the elliptical shape. That's when we have to check for the linearity, normality, and the equivariance, right?
Okay.
That's the beginning part, and then we repeat almost the same thing, but this time we use the residual.
Use the residual. Yes.
Yeah, here I'm trying to understand actually what's the difference between the first one using the observed data, and the second one using the residual. Yeah.
Okay. So for simple linear regression, both methods will produce similar result, right? For simple linear. But for multiple linear regression, you cannot use the X and Y scatter plot. All assumptions need to be made based on the residual diagnostics.
Okay, so all right. Okay.
So I'm just showing the relationship between scatter plot of X and Y, and also the scatter plot of XP and also YR.
Okay,
the
so
residual scatter plot based on residual.
So residual is more important in multiple linear regression,
Yes.
but for
Yes.
Okay.
Okay, so in the subsequent topics on linear regression, logistic regression, on survival analysis or other regression, okay, so all assumption checking will be made based on residual. Okay, so it means that when the residual can reflect the original data. Okay, but for multiple linear regression, you cannot visualize multiple variable using one scatter plot, right? Okay, because in multiple linear regression, it involves more than one independent variable. Okay, so you cannot visualize the relationship based on simple scatter plot. So that's why we rely on residual diagnostics.
Okay, thank you. My other question is, actually, I'm just wondering, why are there so many assumptions for one statistical model? Is it because of the mathematical model that is designed for the statistical model?
Yes, based on statistics, based on mathematical model, based on the mathematical theories. Okay, for example, I show you one example. Okay, like okay, like this one. So X and Y, right? So if we plot a regression line based on this data, okay, we can use the regression line is valid throughout the entire line of X, right? Okay. Why? Because the relationship is linear. Okay. If the relationship is non-linear, but if we do prediction based on linear regression, so we are not going to obtain a correct prediction. Like for example, like this one, it has a curvy linear relationship. But if we develop a linear regression model, then what we predict here, there's lots of error, lots of prediction error over here, right? Okay. So the prediction line becomes better here, and when the observation deviates, when the curve is much prominent, so our prediction become less accurate, right? Okay.
Okay.
Similar thing over here, the prediction error is very small at the initial part, and as the value of X increase, the error in prediction become more prominent, right? Much higher prediction, much higher error. So that's why it is important that the assumption of linearity, assumption of normality, and also assumption of equal variance is fulfilled. So in order to say that the result, the prediction, whatever prediction we make, it will be valid. Yeah?
Okay, all right, got it. Thank you.
Okay.